All right, let's talk about how to find the rate law given some information. There's kind of three different ways that you can get the rate law given the information. Here in this one's called finding the rate law from initial rates. Really just means it's the rate here is measured at right when the reaction begins. When you start it up, when you mix the two things together, you measure the rate. Now the rate will decrease over time as our reactants are used up. A and B are used up in this sort of set of information. When that's used up, the concentration is going to decrease, and if concentration decreases in general, rate's going to decrease. So the rate will change over time. So this is all measured at initial rates. So a couple things when you're given a bunch of this information, you want to make sure that you are looking for some particular things. You're looking for when things change um, and when things are held constant and when they stay the same. So if we look at this, we can look in between trial 1 and trial 2. The thing that changes is that right there. This goes from 1 molar to 2 molar. So we are doubling the concentration of A, but for B, the concentration stays the same. And we have a change in the rate as well. So we kind of have three different options for what our rate order could be. It could be zeroth order. What zeroth order means is that if I change the concentration, there's no change in rate. So the rate doesn't change. Maybe that collision happens in the slow step, and so it's not going to change the rate overall. Then you have first order. First order means that it's a 1-to-1 ratio. What I mean by that is if the concentration is doubled and the rate also doubles, it's first order. If the rate triples, or excuse me, if the concentration triples and the rate triples as well, it's first order. It could even be the rate goes up by a factor, or the concentration goes up by a factor of 0.25, and the rate goes up by a factor of 0.25. It's just, they just have to match. Then the other one that's talked about in AP chemistry is second order. And second order means that it's a 1 to 1 squared ratio. What I mean by that is whatever you do to the concentration, if the square of that factor happens to the rate, then it is second order. So if you were to double the concentration, the rate would go up by a factor of 2 squared, or 4. If you were to triple the concentration, the rate would go up by a factor of 9, which would be 3 squared. So let's look at this reaction, or this set of trials that we have for this reaction. From 1 to 2, we double the rate here, and this needs to be held constant. So it goes from 0.5 to 0.5, doesn't change. It's really important that when you're writing out these ones, you are saying that like um, from 1 to 2, the concentration of B is constant. So you have to say that which one's being held constant. The concentration of A is doubled. And then we have to look at what happens to the rate. So from here to here, we go from 2 times 10 to the negative fourth to 4 times 10 to the negative fourth. So it goes up by a factor of 2. So this is doubled, this is doubled. So the rate is doubled. Therefore, it's first order. So that's sort of the work you should be showing for something like this, just using table logic. There is a mathematical way of doing it, but I think the mathematical way of doing it is very complicated, so not going to really want to worry about that. All right, now we want to see when B changes. So B goes from 0.5 to 1, but we want to have A held constant. So we don't want to use trial 1 and 3 because both of them are changing. This one's going from 1 to 2, this one's going from 0.5 to 1. We want to use trial 2 and 3 because it's constant here and it's changing here. So we know that whatever happens to the rate is going to be due to the B changing, not the A changing. So we're going to write this up just like we did the last one. So from 2 to 3, concentration of A is constant. Concentration of B is double. Rate is what? We go from 4 times 10 to the negative fourth to 1.6 times 10 to the negative third. Now, I know that it goes up by a factor of 4. That's because I'm good at that scientific notation thing. The other way of writing this is 16 times 10 to the negative fourth. So it goes from 4 times 10 to the negative fourth to 16 times 10 to the negative fourth. That is being multiplied by a factor of 4. You can also do it in your calculator. 1.6 times 10 to the negative third divided by 4 times 10 to the negative fourth. Hey, look, goes up by a factor of 4. We would call that being quadrupled. So it is quadrupled. So therefore, so if it's doubled, this is quadrupled. Quadrupled is 2 squared, and it's second order. Now this means first order with in terms of A, second order in terms of B. So if you are asked to write out what a rate law is, it's going to look like this. It's going to be rate is equal to K times the concentration of A, and A is first order, times the concentration of B, and B is second order. So this is your rate law. Now, we just have to, overall, we could say that this is a third order reaction because we have a 1 and a 2, so it's a total of 3. Add that up. If you're asked to find K, all you have to do is plug in any of these values, plug those back into the equation. We have the initial rate, we have each of the concentrations. All you have to do is then calculate K. I think we can do that on our own. So it's not too terribly difficult to do that, but you do want to make sure that K has the correct units. Here it says that the rate is in molarity per second. If it's in molarity per second, this has to be in molarity per second. So this I'm writing the units here, just to make sure that things cancel out. So A we know is going to be molarity. B is molarity squared. So total over here, if these are multiplied together, we have 3 molarities. We only need 1 molarity on the top. We already have 3. So the rate constant needs to have 2 molarities down below in order to cancel. And it also has to have a seconds down below in order to make sure it's in the right. So the units of K are going to be 1 over molarity squared times seconds in order to make the units cancel. So that's one way of finding out the rate law. I will say that the initial rate sort of process, given this data, doesn't come up very often on multiple or on free responses. Comes up more often on multiple choice, but still something that we need to know because you still may have to use that logic. So another way of doing it is getting a concentration versus time data. So you're going to be given a concentration for a reaction and then sort of comparing that to time as you go. So some of the things we need to know about this is determining the rate order is really about which graph is linear. If the concentration versus time graph is linear, then it is 0th order. If the ln of the concentration versus time graph then it's first order. And then lastly, if it's the 1 over versus concentration versus time graph, then it's second order. So that's how we do that. Now, I haven't seen on any of the AP exams after it has been redesigned where you actually have to like make these graphs using your calculator, although we may have practiced that this year. I don't believe we actually have to do that. Um, Normally the graphs are given to you, and you, if like you're using these as reasonings, you do need to say the ln of concentration versus time graph. Um, so you want to make sure you include this language, ln of concentration versus time graph. 1 over concentration versus time graph. Don't say that is just 1 over concentration is linear. You have to say it's 1 over concentration versus time. You have to give whatever the dependent variable is. So let me give an example of this problem. This comes from the 2019 AP exam. It's kind of hard to see with the setup here, but that's okay. We have nitrogen dioxide decomposing into nitrogen monoxide and oxygen here. And then we have graphed on each one of these. This is concentration, this is 1 over concentration, and this is ln of concentration versus time. Now, if you are having trouble determining if something is linear, what you need to do is you just need to have a straight edge, like a sheet of paper or something like that, and then that's going to help you determine whether or not it's linear. So if you can see here, I'm holding up this sheet of paper to it, and it's going right along there. Let me see if I can find a different sheet of paper. Got some markers here. So you can see that I'm covering up half of it. That's not very linear, right? That's not a very linear graph. So we know that it's not the regular concentration versus time graph. We know that that's not correct. The L or the 1 over versus 1 over concentration versus time. It's pretty linear. And then we have the ln of concentration versus time. That's not very linear comparatively. So probably not the ln, so it's got to be the 1 over. So without reading anything, we know that it's going to be second order because the 1 over concentration versus time graph is the one that's linear. So A says to explain how the graphs indicate that the reaction is second order. Well, you would say that the 1 over concentration of NO2 versus time graph is linear. And that's all you would have to say. That would be a perfectly fine answer for a question like this. You would not need to go in tremendous detail. And then B says, write the rate law for the decomposition of NO2. Well, the rate law would be rate is equal to K times the concentration of NO2 to the second power because it is second overall, or second order. And that's it. That's all you'd have to do for that. You don't need to explain anything. When you're doing these problems, you're just answering the question. Now there's another question over this, but that's over mechanisms on the second part there. Then the last way of doing that is half-life. Half-life in kinetics also comes up frequently, and I think it's coming up more often on the AP exam. I'll give you an example problem from I think the 2015 exam that has a half-life problem on it. The way to sort of think about this is always do the first order one first. Um, so if the reaction is first order, it has a stable half-life. Essentially, you can solve for the half-life. You know what the half-life is, and you can find the half-life for that reaction, or for that sort of particular case. If it's a zeroth order or second order, the half-life actually changes. So for zeroth order, the half-life gets smaller. And for a second order reaction, the half-life gets larger. You'll never be able to actually do a half-life or calculate a half-life for a zeroth order or second order because it changes. You'll only ever have to deal with the half-life for first order reactions because that's the only one that actually has a real half-life. Um, this comes up quite frequently on graphs, but sometimes on the data you should also be able to kind of pick out and realize which one is the stable one and why that is. So let's go to the question. Oh, you really can't see that. I can kind of try to show you this here. So if this is the 2017 exam. This is question, I think 3, the end of question 3. Here, this is 0.1000. This is 0.07, 0.05, 0.354, 0.0250, 0.3177, 0.0125. And then graphed is the concentration versus time graph. So we should be able to, maybe if I do this will help. Yeah, that helps a little bit. All right, so we can see that going from 1 to 5, half of it's gone. And then going from 0.05 to 0.025, that's another half. And then going from 0.025 to 0.0125, that's another half. So essentially, this is the time it takes for half of it to disappear. And that is 10 hours. That is another 10 hours. And hey, look, that's another 10 hours. Hey, look, the half-life stays the same, so we know that the reaction is first order. So the question says, the student proposed that the rate law is rate is equal to K times the concentration of this term. Um, and it's to the first. So I says to explain how the data supports the student's proposed rate law. Well, um, now it's really important that you say the data supports. You don't want to say that the ln versus time graph is linear, right? Because that's not what's given to us. What's given to us is the data and the graph, right? And the graph is a concentration versus time, not the ln of concentration versus time. So you have to use the data to tell us what that is. So you would say because the half-life stays the same, it's first order. That's all you really need to say. You just need to say that because the half-life is consistent, it's always 10 hours, that it's going to be a first order reaction. So it says using the proposed rate law and the student's results to determine the value of the rate constant K, include units for your answer. So we are trying to find the value of K. Well, we don't know the rate, so we can't use this in order to determine that. But on your equation sheet, there is an equation that's given to you that is going to help you do this. This is the only time you're ever going to use this equation, and that is, it says T1 half, which is the half-life of something, is equal to 0.693 over K. It's the only time you ever use this equation because it's the half-life is equal to this term divided by K, which is the rate constant for this reaction. All we're going to do now is plug in some numbers and then get our answer. We know that the half-life time is 10 hours, and that's equal to 0.693 over K. So to solve for K, we can kind of just switch those. And so K is going to be equal to this divided by 10 is 0.0693, and the units are going to be 1 over hours. And that is your K term. So there's a lot of different ways that you can find rate order. You can use the initial rates. You can use the graphs using sometimes those are called integrated rate laws. Um, or you can use half-life to determine them. But there are definitely many different ways that you can find the rate order for a reaction.